Hi, my name is Georgi Radov, and a system level circuit of an oscillator is given. The G block is a transconductor with input voltage V in and output current I out and transconductance G. The parameters of the circuit are given, and the question is what should be the value of G for amplitude-stable oscillations. Now, in a previous video, I will put at the end the link to it. We analyzed this circuit here and derived an expression. So basically, the analysis was based on writing the Kirchhoff current law for these two nodes here, this one and this one. This allowed us to write an expression and reach a form of this expression that depends only on one voltage, V in only. This is how we eliminated V out from the Kirchhoff current law at this node. Because we assumed that there are oscillations, this means that V in for this particular frequency of oscillation is not zero. So we are allowed to divide everything by V in. And then we have an expression which is this one, which is a complex expression equal to 0. It has an imaginary part and a real part. For this complex expression to be 0, then both the real part and the imaginary part must be 0. By equating the imaginary part to 0, we will get the frequency of oscillation. So this is the frequency of oscillation. Now, this is the important part that we need for our problem to find the transconductance G. So I will copy this part simply and I will simply paste it here so that I can start from this expression. Alright, and now my goal is to find G in order to maintain the frequency of oscillation. Very intuitively, you can say that G will have to compensate the losses of R. So G will have to be 1 over R. Now, why is this? Let's see. This is the frequency of oscillations. So this. Now we consider that for this expression to be 0, the real part should also be 0. For W, for omega, we will use the expression for the frequency of oscillation. So now I can write 1 minus omega square, and omega square is 2 divided by LC, times LC, minus GR is equal to 0. LC will cancel out, so GR will be minus 1, and G will be 1 over R. With the values that we have, R is 5k, 1 divided by 5 10 to the power of 3, k it will be 0.2 millisiemens. So this will be 0. This answer. And if G is 0.2 millisiemens, it will exactly compensate for the losses that we have in the resistor, and hence we will have frequency stable oscillation, just satisfying the Barkhausen criteria for oscillations. Thank you very much.